Hello and welcome. Today, we're diving into one of the biggest, most fundamental challenges in all of modern electronics, the short-channel challenge in MOSFET transistors. This is the tiny, microscopic battle that literally defines the speed and power of every single device you own. So at its core, the transistor is the basic switch that powers our entire digital world. In a perfect world, it's a perfect switch, right? Instantly on, instantly off. But, and this is a big but, in the real world, it's not quite perfect. And that little imperfection is where all the incredible complexity and all the amazing innovation really begins. So, what exactly is a MOSFET? Well, think of it as the microscopic workhorse inside every chip you've ever used. It's basically a tiny gate for electricity. You apply a little bit of voltage to its control terminal, which is called the gate, and that either opens or closes the path for current to flow. Now imagine billions of these all working together. That's what creates the logic that lets our computers actually compute. Okay, so here's our game plan for this explainer. We're going to start by looking at the ideal transistor. Then we'll see what happens when we shrink it way, way down. We'll find out why they have such a hard time turning all the way off, how they start messing with each other, and finally, we'll get into the serious long-term damage caused by something called hot carriers. So let's ask that question again. Is the transistor a perfect switch? Well, in our classic textbook models, it behaves beautifully. You apply a voltage that's above a certain threshold and boom, it conducts. You drop below that threshold and the current just stops completely. This simple on-off binary behavior is the bedrock of all digital logic. But here's the catch. For decades, the name of the game in electronics has been making these switches smaller and smaller. It's a process we call scaling. And as we shrink that channel, that's the distance the current actually has to travel, all these strange new physical effects start popping up. Things our classic models just never saw coming. And this right here really gets to the heart of the problem. You see, the old long-channel MOSFET was this well-behaved, totally predictable component where the gate had absolute control. But the modern short-channel MOSFET, it's a completely different beast. It's where the neat, clean rules of electronics smash right into the messy, complicated reality of physics at the nanoscale. So what's the very first major problem that shows up? It's that the switch, it doesn't really switch all the way off anymore. It leaks. And when you have billions of these tiny leaks all happening at once, well, you've got a really serious power problem. This leakage has a name. It's called subthreshold conduction. So even when the gate voltage is below that turn-on threshold, a tiny little trickle of current still manages to get through. It's kind of like a faucet that you've turned off as hard as you can, but it still drips. Now, one drip is no big deal, right? But a billion dripping faucets? That's not a drip, that's a flood. And in this case, it's what's dreaming your battery. So how do engineers even measure how off something is? They use a metric called the subthreshold slope. It basically tells us how much you have to change the gate voltage to cut that leakage current down by a factor of 10. To use our faucet analogy again, it's like a measure of how sensitive the handle is. And this means that chip designers are obsessed with getting the smallest slope value they possibly can. A low number here means a really sharp turnoff. It lets the switch go from leaking to totally off with just a tiny little nudge of voltage. And that is absolutely critical for making the low-power, high-performance chips that we have in our phones and laptops today. You know, this whole leakage problem is tied directly to the exact moment the transistor turns on. So that brings up a super important question for the engineers. How on earth do you precisely set that threshold voltage to begin with for billions of transistors all at the same time? Well, the answer sounds like it's straight out of science fiction. It's a process called ion implantation. Engineers literally shoot a beam of charged atoms, ions, right into the silicon surface. And by controlling the exact dose of these implanted dopants, they can tweak the electrical properties of the channel and set that threshold voltage to the precise value they need. It's incredible stuff. But even with that amazing level of control, shrinking the transistor just creates a whole new can of worms. When you squeeze the source and drain terminals closer and closer together, they actually start to interfere with the channel that's in between them, and that undermines the gate's authority. These interference problems usually fall into three main buckets. There's charge sharing, a phenomenon called Drain-Induced Barrier Lowering, or DIBL for short, and then a really nasty one called subsurface punch-through. Let's break each of those down. All right, first up is charge sharing. So imagine the gate's job is to push open a heavy door.
Now, in a short channel, the source and drain are so close together, they basically start leaning on that door from the other side, helping the gate open it. This means the gate has to do less work, and the transistor turns on at a lower voltage than it was designed to, which, as you can imagine, can totally throw off a circuit's timing.
Next up is DIBL. Okay, picture an energy hill that electrons from the source have to climb over to get into the channel. The gate's job is to control the height of that hill. But in these tiny devices, the high voltage at the drain can actually reach across the channel and start lowering the hill all by itself. This makes it way easier for electrons to leak across, which just makes that subthreshold leakage problem even worse. And that leads us to the most severe effect of all, punch-through. This is what happens when DIBL just goes completely off the rails. The drain's influence expands so much that it just wipes out the barrier entirely, basically connecting itself directly to the source. And at that point, a huge uncontrolled current can just flood through, and the gate has completely, totally lost control.
Now, this punch-through often happens deep under the surface. There's this electrically empty zone called a depletion region that spreads out from the drain, kind of like a tunnel. It keeps expanding underneath the main channel until it finally reaches the source. And once that connection is made, the gate is just completely bypassed. The device has failed.
Okay, this brings us to a final, really long-term problem. All of these effects we've talked about, they're driven by unbelievably strong electric fields that are packed into these tiny, tiny spaces. And these high fields create a whole new kind of danger, one that threatens the physical lifespan of the chip itself. And this danger comes from something called hot carriers. Now, this term doesn't actually have anything to do with temperature. It's all about energy. You have these electrons racing across that super short channel, and they get accelerated by this intense electric field, gaining a massive amount of kinetic energy. They basically become microscopic bullets ricocheting around inside the transistor.
And these energetic little bullets cause a ton of damage. They can slam into the silicon lattice and create unwanted currents down in the substrate. Some are so energetic, they can literally blast right through the thin oxide layer and create a gate current, physically damaging the transistor. And over time, all this cumulative damage degrades the device's performance until one day it just fails. So at the end of the day, managing these hot carrier effects is one of the most critical challenges in making sure our electronics actually last. It's a constant battle for engineers who are fighting against the very same physics that makes these chips so incredibly fast in the first place. And that really gets to the heart of what modern engineering is all about. You see, you can't just get rid of these quantum effects. The goal is to understand them so deeply that you can balance them. You might trade just a tiny bit of leakage for a lot more speed, or maybe you sacrifice a little performance to get better long-term reliability. It's a really intricate dance with the laws of physics. Which, of course, leaves us with the ultimate question. As these transistors continue to shrink down to the size of just a handful of atoms, these challenges get exponentially harder to solve. So what comes next? Are we talking about new materials? Entirely new ways of building these devices? Well, that is the frontier that engineers are exploring right now.